Hello, my name is Adam Lilly, and today I'll be summarizing the paper Tectonic-Shift, a composite storage fabric for large-scale machine learning training published by Mark Zhao. This paper addresses a major bottleneck inside Meta's ML training infrastructure, the challenge of delivering extremely high read bandwidth while keeping storage power efficient. Their previous HDD-only system, called Tectonic, struggles to keep up with the rapid growth of ML workloads. Tectonic-Shift introduces a new hybrid storage approach that dramatically improves performance and efficiency. In this presentation, I'll explain the problem, the proposed solution, how the architecture works, and the results they achieved. Modern ML training, especially recommendation models, needs to read massive datasets, often petabytes, from storage at extremely high speeds. Meta's training clusters, which contain thousands of GPUs, require tens of terabytes per second of sustained read bandwidth. But storage systems haven't kept up with that demand. Even though HDDs provide huge capacity, they offer very poor random I/O performance and poor I/O per watt. As training jobs got larger, the storage layer became the bottleneck, slowing down training and consuming too much power. This created an urgent need for a more balanced and efficient storage architecture. Tectonic, Meta's previous storage system, used clusters of HDDs to store and serve training data. The problem was that HDDs scale capacity much faster than bandwidth. So to meet I/O demand, Meta had to employ 10 times more HDDs than needed, wasting power just to get enough read throughput. In fact, the storage system was starting to consume more power than the GPUs doing the training. This design simply wasn't sustainable as ML growth continued. Tectonic-Shift solves this imbalance by combining HDDs with a flash-based layer called Shift. HDDs remain responsible for providing large storage capacity, while Flash absorbs the majority of read I/O. Flash offers much higher I/O per watt, so this hybrid approach provides the best of both worlds. The key idea is to serve most training reads from fast Flash while using HDDs only as a long-term durable backend. The most important innovation in Tectonic-Shift is its application-aware caching layer. Instead of relying on simple LRU or FIFO caching, which fails for large streaming ML datasets, Shift uses knowledge about each training job. Training jobs declare exactly which tables, partitions, and features they will read. Shift uses this metadata to predict future access patterns and only cache data that will see reuse across jobs. This greatly reduces cache thrashing and maximizes the amount of I/O served from Flash. Shift also dynamically adjusts admission and eviction thresholds to stay within SSD endurance limits. When a training job issues a read, the client library first checks whether the requested block is eligible for Shift. If it is, the request is routed to a Flash node, which checks whether the needed segments are already cached. If they are, the data is returned immediately from Flash. If not, Shift decides whether the segment should be cached based on priority rules before fetching them from the HDD cluster. Everything is transparent to users. Training pipelines don't need to change anything. Shift is decentralized, fault-tolerant, and integrates directly into the existing Tectonic API. In evaluation, Tectonic-Shift absorbed 1.5 times to 3.28 times more I/O than a standard LRU flash cache, depending on the workload pattern. In production, it reduced storage power consumption by 29%, which is a massive improvement at meta scale. The system effectively balances capacity and bandwidth, eliminates unnecessary HDD over-provisioning, and keeps up with the explosive ML growth. Overall, Tectonic-Shift represents a major step forward in designing storage systems tailored specifically for large-scale machine learning.